Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Data Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You have data pipelines running on BigQuery, Dataflow, and Dataproc. You need to perform health checks and monitor their behavior, and then notify the team managing the pipelines if they fail. You also need to be able to work across multiple projects. Your preference is to use managed products or features of the platform. What should you do? The options are: Option A, export the information to cloud monitoring and set up an alerting policy. Option B, run a virtual machine in Compute Engine with Airflow and export the information to cloud monitoring. Option C, export the logs to BigQuery and set up App Engine to read that information and send emails if you find a failure in the logs. Option D, develop an App Engine application to consume logs using GCP API calls and send emails if you find a failure in the logs.
To arrive at the correct answer, we focus on the keywords, monitor their behavior, notify the team, across multiple projects, managed products or features.
The correct answer is Option A, export the information to cloud monitoring and set up an alerting policy.
Why is this correct? A. Cloud monitoring natively aggregates metrics and health checks across multiple projects. Alerting policies provide a fully managed platform feature to automatically notify teams upon failure. Why are the others incorrect? B. Running Airflow on a Compute Engine virtual machine involves managing infrastructure yourself, which violates the requirement to use managed products. C. Building a custom alerting system with BigQuery and App Engine requires unnecessary development and maintenance instead of using built-in managed features. D. Developing a custom App Engine application is an unmanaged approach that adds overhead when native managed monitoring features exist.
You are working on a linear regression model on BigQuery ML to predict a customer's likelihood of purchasing your company's products. Your model uses a city name variable as a key predictive component. In order to train and serve the model, your data must be organized in columns. You want to prepare your data using the least amount of coding while maintaining the predictable variables. What should you do? The options are: Option A, create a new view with BigQuery that does not include a column with city information. Option B, use SQL in BigQuery to transform the state column using a one-hot encoding method and make each city a column with binary values. Option C, use TensorFlow to create a categorical variable with a vocabulary list. Create the vocabulary file and upload that as part of your model to BigQuery ML. Option D, use Cloud Data Fusion to assign each city to a region that is labeled as 1, 2, 3, 4, or 5, and then use that number to represent the city in the model.
To arrive at the correct answer, we focus on the keywords, linear regression model on BigQuery ML, city name variable, organized in columns, least amount of coding.
The correct answer is Option B, use SQL in BigQuery to transform the state column using a one-hot encoding method and make each city a column with binary values.
Why is this correct? B. One-hot encoding translates categorical variables into binary columns, satisfying the data structure requirement. Using native SQL in BigQuery achieves this with minimal coding compared to external tools, maintaining the predictive variables effectively. Why are the others incorrect? A. Removing the city information drops a key predictive component, violating the requirement to maintain the predictable variables. C. Relying on TensorFlow and uploading a vocabulary file introduces significant complexity and extra coding, contradicting the goal of using the least amount of coding. D. Using Cloud Data Fusion to map cities to arbitrary region numbers applies label encoding, which is inappropriate for linear regression as it implies a mathematical order where none exists.
You work for a large bank that operates in locations throughout North America. You are setting up a data storage system that will handle bank account transactions. You require ACID compliance and the ability to access data with SQL. Which solution is appropriate? The options are: Option A, store transaction data in Cloud Spanner. Enable stale reads to reduce latency. Option B, store transaction in Cloud Spanner. Use locking read-write transactions. Option C, store transaction data in BigQuery. Disable the query cache to ensure consistency. Option D, store transaction data in Cloud SQL. Use a federated query BigQuery for analysis.
To arrive at the correct answer, we focus on the keywords, locations throughout North America, bank account transactions, ACID compliance, access data with SQL.
The correct answer is option B, store transaction in Cloud Spanner. Use locking read-write transactions.
Why is this correct? B. Cloud Spanner is designed for multi-region scale, North America, and provides full SQL support with strong consistency. Locking read-write transactions ensure ACID compliance, making it ideal for strict financial transaction processing. Why are the others incorrect? A. Stale reads allow reading slightly outdated data to reduce latency, which is inappropriate for financial transactions requiring strict, up-to-date ACID compliance. C. BigQuery is an OLAP data warehouse designed for analytics, not an OLTP database suitable for processing individual bank account transactions. D. While Cloud SQL provides SQL access and ACID compliance, it is a regional service that does not scale horizontally across multiple regions, North America, as effectively as Cloud Spanner.
A shipping company has live package tracking data that is sent to an Apache Kafka stream in real time. This is then loaded into BigQuery. Analysts in your company want to query the tracking data in BigQuery to analyze geospatial trends in the lifecycle of a package. The table was originally created with ingest date partitioning. Over time, the query processing time has increased. You need to implement a change that would improve query performance in BigQuery. What should you do? The options are: Option A, implement clustering in BigQuery on the ingest date column. Option B, implement clustering in BigQuery on the package tracking ID column. Option C, tier older data onto cloud storage files and create a BigQuery table using cloud storage as an external data source. Option D, recreate the table using data partitioning on the package delivery date.
To arrive at the correct answer, we focus on the keywords, analyze geospatial trends in the lifecycle of a package, ingest date partitioning, improve query performance.
The correct answer is option B, implement clustering in BigQuery on the package tracking ID column.
Why is this correct? B. Clustering the table by the package tracking ID collocates data for the same package within each partition. This directly optimizes queries analyzing the lifecycle of a specific package by reducing the amount of data scanned, significantly improving query performance. Why are the others incorrect? A. The table is already partitioned by ingest date. Clustering on package tracking ID is much more effective because the lifecycle analysis queries will filter or group by the package ID, benefiting greatly from collocated data. C. Moving older data to cloud storage and querying it as an external table generally decreases performance compared to native BigQuery storage, which leverages a highly optimized, fully managed columnar format. Why are the others incorrect? D. Partitioning by delivery date is less effective for real-time tracking, as the delivery date is often unknown until the end of the lifecycle. The existing ingest date partitioning combined with clustering is optimal.
Your company currently runs a large on-premises cluster using Spark, Hive, and HDFS in a colocation facility. The cluster is designed to accommodate peak usage on the system. However, many jobs are batch in nature, and usage of the cluster fluctuates quite dramatically. Your company is eager to move to the cloud to reduce the overhead associated with on-premises infrastructure and maintenance and to benefit from the cost savings. They are also hoping to modernize their existing infrastructure to use more serverless offerings in order to take advantage of the cloud. Because of the timing of their contract renewal with the colocation facility, they have only 2 months for their initial migration. How would you recommend they approach their upcoming migration strategy so they can maximize their cost savings in the cloud while still executing the migration in time? The options are: Option A, migrate the workloads to Dataproc plus HDFS, modernize later. Option B, migrate the workloads to Dataproc plus cloud storage, modernize later. Option C, migrate the Spark workload to Dataproc plus HDFS, and modernize the Hive workload for BigQuery. Option D, modernize the Spark workload for Dataflow and the Hive workload for BigQuery.
To arrive at the correct answer, we focus on the keywords Spark, Hive, and HDFS, fluctuates quite dramatically, only 2 months for their initial migration, maximize their cost savings.
Correct answer is option B, migrate the workloads to Dataproc plus cloud storage, modernize later.
Why is this correct? B. Migrating to Dataproc with cloud storage decouples compute and storage, maximizing cost savings for fluctuating batch workloads. Delaying modernization ensures they meet the strict 2-month deadline. Why are the others incorrect? A. Using HDFS couples storage and compute, requiring persistent clusters that cannot be easily scaled down or turned off, limiting potential cost savings. C. Modernizing Hive to BigQuery requires significant code and schema changes, which cannot be feasibly completed within the short 2-month migration window. D. Completely modernizing both Spark to Dataflow and Hive to BigQuery involves extensive refactoring that is impossible to achieve within the strict 2-month timeframe.
You work for a financial institution that lets customers register online. As new customers register, their user data is sent to pub/sub before being ingested into BigQuery. For security reasons, you decide to redact your customer's government-issued identification number while allowing customer service representatives to view the original values when necessary. What should you do? The options are: Option A, use BigQuery's built-in AEAD encryption to encrypt the SSN column. Save the keys to a new table that is only viewable by permissioned users. Option B, use BigQuery column-level security. Set the table permissions so that only members of the customer service user group can see the SSN column. Option C, before loading the data into BigQuery, use Cloud Data Loss Prevention (DLP) to replace input values with a cryptographic hash. Option D, before loading the data into BigQuery, use Cloud Data Loss Prevention (DLP) to replace input values with a cryptographic format-preserving encryption token.
To arrive at the correct answer, we focus on the keywords user data is sent to pub/sub before being ingested into BigQuery, redact your customer's government-issued identification number, allowing customer service representatives to view the original values.
The correct answer is option D, before loading the data into BigQuery, use Cloud Data Loss Prevention (DLP) to replace input values with a cryptographic format-preserving encryption token.
Why is this correct? D. Cloud DLP's deterministic encryption, tokenization, replaces sensitive data with a format-preserving token before it reaches BigQuery. Authorized customer service representatives can reverse this process, detokenize, to view the original government-issued identification number. Why are the others incorrect? A. AAD encryption is performed within BigQuery, meaning data is ingested before being encrypted. Furthermore, storing encryption keys in a BigQuery table is not a secure key management practice. B. Column-level security restricts who can query the column in BigQuery, but it does not redact or transform the sensitive data before or during ingestion into BigQuery. C. A cryptographic hash is a one-way function. Once the data is hashed, it cannot be reversed, meaning customer service representatives would be unable to view the original values.
You are migrating a table to BigQuery and are deciding on the data model. Your table stores information related to purchases made across several store locations and includes information like the time of the transaction, items purchased, the store ID, and the city and state in which the store is located. You frequently query this table to see how many of each item were sold over the past 30 days and to look at purchasing trends by state, city, and individual store. How would you model this table for the best query performance? The options are: Option A, partition by transaction time, cluster by state first, then city, then store ID. Option B, partition by transaction time, cluster by store ID first, then city, then state. Option C, top-level cluster by state first, then city, then store ID. Option D, top-level cluster by store ID first, then city, then state.
To arrive at the correct answer, we focus on the keywords: time of the transaction, past 30 days, by state, city, and individual store.
The correct answer is option A, partition by transaction time, cluster by state first, then city, then store ID.
Why is this correct? A. Partitioning by transaction time optimizes queries filtering on the past 30 days. Clustering hierarchically by state, then city, then store ID ensures efficient data sorting and filtering from macro to micro levels, matching the geographic query access patterns. Why are the others incorrect? B. While partitioning by time is correct, clustering by store ID first reduces query performance for state and city filters, as BigQuery clustering requires prefix matching for optimal filtering. C. This option lacks partitioning by transaction time, which is crucial for efficiently filtering queries bounded by a specific time range, such as the past 30 days. D. It omits time-based partitioning necessary for the 30-day filter and incorrectly orders the clustering columns from granular to broad, which prevents efficient prefix filtering by state or city.
You are updating the code for a subscriber to a pub/sub feed. You are concerned that upon deployment the subscriber may erroneously acknowledge messages, leading to message loss. Your subscriber is not set up to retain acknowledged messages. What should you do to ensure that you can recover from errors after deployment? The options are: Option A, set up the pub/sub emulator on your local machine. Validate the behavior of your new subscriber logic before deploying it to production. Option B, create a pub/sub snapshot before deploying new subscriber code. Use a seek operation to redeliver messages that became available after the snapshot was created. Option C, use cloud build for your deployment. If an error occurs after deployment, use a seek operation to locate a timestamp logged by cloud build at the start of the deployment. Option D, enable dead lettering on the pub/sub topic to capture messages that aren't successfully acknowledged. If an error occurs after deployment, redeliver any messages captured by the dead letter queue.
To arrive at the correct answer, we focus on the keywords: erroneously acknowledge messages, not set up to retain acknowledged messages, recover from errors after deployment.
The correct answer is option B, create a pub/sub snapshot before deploying new subscriber code. Use a seek operation to redeliver messages that became available after the snapshot was created.
Why is this correct? B. Creating a pub/sub snapshot captures the unacknowledged messages. Since the subscriber doesn't retain acknowledged messages, a snapshot allows you to use a seek operation to revert to that state and recover messages erroneously acknowledged by the new code. Why are the others incorrect? A. Testing locally with the pub/sub emulator is a preventative measure, but it does not provide a mechanism to recover from errors once the code is actually deployed to production. C. Seeking to a timestamp requires the subscription to be configured with retain acknowledged messages enabled. Because the question specifies this is not set up, seeking to a timestamp will not recover the messages. Why are the others incorrect? D. A dead letter queue captures messages that fail to be processed and remain unacknowledged. If the new subscriber erroneously acknowledges messages, they will bypass the dead letter queue and still be lost.
You work for a large real estate firm and are preparing 6 terabytes of home sales data to be used for machine learning. You will use SQL to transform the data and use BigQuery ML to create a machine learning model. You plan to use the model for predictions against a raw dataset that has not been transformed. How should you set up your workflow in order to prevent skew at prediction time? The options are: Option A, when creating your model, use BigQuery's transform clause to define pre-processing steps. At prediction time, use BigQuery's ml.evaluate clause without specifying any transformations on the raw input data. Option B, when creating your model, use BigQuery's transform clause to define pre-processing steps. Before requesting predictions, use a saved query to transform your raw input data, and then use ml.evaluate. Option C, use a BigQuery view to define your pre-processing logic. When creating your model, use the view as your model training data. At prediction time, use BigQuery's ml.evaluate clause without specifying any transformations on the raw input data. Option D, pre-process all data using Dataflow. At prediction time, use BigQuery's ml.evaluate clause without specifying any further transformations on the input data.
To arrive at the correct answer, we focus on the keywords: use SQL to transform the data, use BigQuery ML to create a machine learning model, predictions against a raw dataset that has not been transformed, prevent skew at prediction time.
The correct answer is option A. When creating your model, use BigQuery's transform clause to define pre-processing steps. At prediction time, use BigQuery's ml.evaluate clause without specifying any transformations on the raw input data.
Why is this correct? A. BigQuery ML's transform clause embeds pre-processing steps within the model. When invoking prediction or evaluation functions, the exact same transformations are automatically applied to the raw input data, ensuring no training serving skew occurs. Why are the others incorrect? B. Manually transforming raw input data with a saved query before prediction introduces maintenance overhead and the risk of training serving skew if the training and prediction transformation logic diverges over time. C. Using a view for training transformations requires you to manually ensure the identical transformations are applied at prediction time. The raw data won't be automatically transformed, leading to errors or skew. D. Pre-processing with Dataflow separates transformation logic from the BigQuery ML model. To prevent skew, you would need to manually recreate and apply the identical transformations at prediction time, which is complex and error-prone.
You are analyzing the price of a company's stock. Every 5 seconds, you need to compute a moving average of the past 30 seconds worth of data. You are reading data from pub/sub and using Dataflow to conduct the analysis. How should you set up your windowed pipeline? The options are: Option A, use a fixed window with a duration of 5 seconds. Emit results by setting the following trigger: after processing time. Past first element in pane, plus delay of, duration. Standard seconds, 30. Option B, use a fixed window with a duration of 30 seconds. Emit results by setting the following trigger: after watermark. Past end of window. Plus delay of, duration. Standard seconds, 5. Option C, use a sliding window with a duration of 5 seconds. Emit results by setting the following trigger: after processing time. Past first element in pane. Plus delay of, duration. Standard seconds, 30. Option D, use a sliding window with a duration of 30 seconds and a period of 5 seconds. Emit results by setting the following trigger: after watermark. Past end of window.
To arrive at the correct answer, we focus on the keywords: every 5 seconds, moving average, past 30 seconds worth of data.
Correct answer is option D. Use a sliding window with a duration of 30 seconds and a period of 5 seconds. Emit results by setting the following trigger: after watermark. Past end of window.
Why is this correct? D. A sliding window with a duration of 30 seconds and a period of 5 seconds perfectly matches the requirement to compute a moving average over 30 seconds of data, updated every 5 seconds. The trigger ensures results are emitted once data is complete. Why are the others incorrect? A. Fixed windows do not overlap. A 5-second fixed window only captures 5 seconds of data, making it impossible to compute a 30-second moving average, regardless of the trigger. B. A 30-second fixed window computes an average over non-overlapping 30-second blocks. It will not update every 5 seconds as required for the moving average. C. A sliding window with a 5-second duration only encompasses 5 seconds of data per window, failing to capture the required 30 seconds of data for the calculation.
You are designing a pipeline that publishes application events to a pub/subtopic. Although message ordering is not important, you need to be able to aggregate events across disjoint hourly intervals before loading the results to BigQuery for analysis. What technology should you use to process and load this data to BigQuery while ensuring that it will scale with large volumes of events? The options are: Option A. Create a cloud function to perform the necessary data processing that executes using the pub/sub trigger every time a new message is published to the topic. Option B. Schedule a cloud function to run hourly, pulling all available messages from the pub/sub topic and performing the necessary aggregations. Option C. Schedule a batch Dataflow job to run hourly, pulling all available messages from the pub/sub topic and performing the necessary aggregations. Option D. Create a streaming Dataflow job that reads continually from the pub/sub topic and performs the necessary aggregations using tumbling windows.
To arrive at the correct answer, we focus on the keywords pub/subtopic, aggregate events across disjoint hourly intervals, loading the results to BigQuery, scale with large volumes of events.
The correct answer is option D. Create a streaming Dataflow job that reads continually from the pub/sub topic and performs the necessary aggregations using tumbling windows.
Why is this correct? D. Dataflow streaming scales for large event volumes from pub/sub. Tumbling windows natively address the need to aggregate events across disjoint hourly intervals before loading them to BigQuery. Why are the others incorrect? A. Cloud functions triggered by individual messages are stateless and cannot effectively aggregate events across hourly intervals. B. Cloud functions have execution time limits and are not designed to pull and process large volumes of events simultaneously in a single scheduled run. C. A batch Dataflow job is less efficient for continuous pub/sub data. Streaming Dataflow with tumbling windows is the native and optimal way to handle unbounded disjoint interval aggregations.
You work for a large financial institution that is planning to use Dialogflow to create a chatbot for the company's mobile app. You have reviewed old chat logs and tagged each conversation for intent based on each customer's stated intention for contacting customer service. About 70% of customer requests are simple requests that are solved within 10 intents. The remaining 30% of inquiries require much longer, more complicated requests. Which intents should you automate first? The options are: Option A. Automate the 10 intents that cover 70% of the requests so that live agents can handle more complicated requests. Option B. Automate the more complicated requests first because those require more of the agent's time. Option C. Automate a blend of the shortest and longest intents to be representative of all intents. Option D. Automate intents in places where common words such as payment appear only once so the software isn't confused.
To arrive at the correct answer, we focus on the keywords. 70% of customer requests are simple requests that are solved within 10 intents, 30% of inquiries require much longer, more complicated requests. Which intents should you automate first?
The correct answer is option A. Automate the 10 intents that cover 70% of the requests so that live agents can handle more complicated requests.
Why is this correct? A. Automating the most frequent, simple requests first provides immediate ROI by significantly reducing the workload on live agents. allowing them to focus on the complex, longer inquiries that require human intervention. Why are the others incorrect? B. Automating complex requests first is harder, slower, and riskier. While they take more time individually, simple requests account for the vast majority of overall support inquiries. C. Blending short and long intents delays the automation of the most common, easily solved requests, reducing the immediate efficiency gains for the customer support team. D. Basing automation solely on single-word appearances is arbitrary and ignores the clear statistical distribution of simple versus complex intent frequencies established in the prompt.
Your company is implementing a data warehouse using BigQuery, and you have been tasked with designing the data model. You move your on-premises sales data warehouse with a star data schema to BigQuery but notice performance issues when querying the data of the past 30 days. Based on Google's recommended practices, what should you do to speed up the query without increasing storage costs? The options are: Option A, denormalize the data. Option B, shard the data by customer ID. Option C, materialize the dimensional data in views. Option D, partition the data by transaction date.
To arrive at the correct answer, we focus on the keywords: BigQuery, querying the data of the past 30 days, speed up the query without increasing storage costs.
The correct answer is option D, partition the data by transaction date.
Why is this correct? D. Partitioning by transaction date allows BigQuery to scan only the relevant partitions, the past 30 days, significantly speeding up queries without duplicating data or increasing storage costs. Why are the others incorrect? A. Denormalizing data typically increases storage requirements due to duplicated data, which directly violates the requirement to not increase storage costs. B. Sharding by customer ID does not optimize time-bound queries past 30 days, and table sharding is generally an anti-pattern compared to partitioning in BigQuery. C. Materializing dimensional data in views does not significantly improve performance for time-bound queries on large fact tables compared to partitioning.
You have uploaded 5 years of log data to cloud storage. A user reported that some data points in the log data are outside of their expected ranges, which indicates errors. You need to address this issue and be able to run the process again in the future while keeping the original data for compliance reasons. What should you do? The options are: Option A, import the data from cloud storage into BigQuery. Create a new BigQuery table and skip the rows with errors. Option B, create a compute engine instance and create a new copy of the data in cloud storage. Skip the rows with errors. Option C, create a Dataflow workflow that reads the data from cloud storage, checks for values outside the expected range, sets the value to an appropriate default, and writes the updated records to a new dataset in cloud storage. Option D, create a Dataflow workflow that reads the data from cloud storage, checks for values outside the expected range, sets the value to an appropriate default, and writes the updated records to the same dataset in cloud storage.
To arrive at the correct answer, we focus on the keywords: cloud storage, outside of their expected ranges, run the process again in the future, keeping the original data for compliance reasons.
The correct answer is option C, create a Dataflow workflow that reads the data from cloud storage, checks for values outside the expected range, sets the value to an appropriate default, and writes the updated records to a new dataset in cloud storage.
Why is this correct? C. Dataflow provides a fully managed, serverless service for building repeatable data processing pipelines. Writing to a new dataset addresses the out-of-range errors while preserving the original dataset for compliance requirements. Why are the others incorrect? A. Skipping rows removes data entirely rather than addressing the out-of-range errors. Additionally, Dataflow is better suited than BigQuery for creating automated, repeatable data transformation pipelines. B. Using a compute engine instance introduces manual operational overhead for infrastructure management and scaling. A managed service like Dataflow is more efficient for this task. D. Writing the updated records back to the same dataset would overwrite the original data, violating the strict requirement to keep the original data for compliance reasons.
You want to rebuild your batch pipeline for structured data on Google Cloud. You are using PySpark to conduct data transformations at scale, but your pipelines are taking over 12 hours to run. To expedite development and pipeline runtime, you want to use a serverless tool and SOL syntax. You have already moved your raw data into cloud storage. How should you build the pipeline on Google Cloud while meeting speed and processing requirements? The options are: Option A, convert your PySpark commands into Spark SQL queries to transform the data, and then run your pipeline on Dataproc to write the data into BigQuery. Option B, ingest your data into Cloud SQL, convert your PySpark commands into Spark SQL queries to transform the data, and then use federated queries from BigQuery for machine learning. Option C, ingest your data into BigQuery from cloud storage, convert your PySpark commands into BigQuery SQL queries to transform the data, and then write the transformations to a new table. Option D, use Apache Beam Python SDK to build the transformation pipelines, and write the data into BigQuery.
To arrive at the correct answer, we focus on the keywords: structured data, serverless tool, SOL syntax, cloud storage.
The correct answer is option C, ingest your data into BigQuery from cloud storage, convert your PySpark commands into BigQuery SQL queries to transform the data, and then write the transformations to a new table.
Why is this correct? C. BigQuery is a fully serverless enterprise data warehouse that natively supports SQL. Ingesting data from cloud storage and using BigQuery SQL for transformations directly addresses the need for a serverless tool, SQL syntax, and faster processing for structured data. Why are the others incorrect? A. Dataproc is a managed Hadoop and Spark service that requires cluster provisioning and management. It is not a fully serverless tool, which goes against the prompt's requirements. B. Cloud SQL is a relational database service designed for online transaction processing (OLTP) workloads, not for running large-scale batch data transformations or analytical pipelines. Why are the others incorrect? D. Using the Apache Beam Python SDK requires writing procedural Python code, which directly contradicts the requirement to use SQL or SOL syntax for the data transformations.